Okay, my talk is going to be about equilibrium and Newtonian idealization. It first was called equilibrium, Newtonian de-idealization. Then I went in my mind through always switching back between the two words in the talk, and I thought I can't do that. So but it's the same topic, and I'm interested in trying to spell out, broadly speaking, how the notion of equilibrium and the way it's used in reasoning changed with the advent of Newtonian mechanics and its application to problems in celestial mechanics. But I want to say some generic things also in the spirit of the workshop and some common ideas I had with Eugene. So as we all know, and I guess we've also learned in Sarah's wonderful talk, the notion of equilibrium is old, and as you all know from all the talks on the different topics they're going to give, it's widespread. And at least in the history of physics, there's a generic sense of equilibrium that's used just throughout the history of physics, right? And there's some minimal criteria. We think of systems that are in equilibrium to be at least stationary over time, usually. And they are stationary in virtue of some kind of balance relation between some properties that can explain that stationarity. But what we tend to think is that, of course, that is not sufficient to actually use the concept of equilibrium to model and solve problems with regard to any physical system, and think of the whole array of systems in which equilibrium reasoning is used, that we describe as being in states of equilibrium: bridges, pulleys, orbits, shapes of planets, compound pendulums, the steam engines. All these things are variously said to be in some states of equilibrium, but how we spell out what that means is different in all these cases. So such that throughout the history of physics, this generic understanding of equilibrium that we all know and use all the time was then further specified with the help of different physical principles. And again, think of things like the lever, Newtonian forces, potential energy, the law of large numbers, etc., that make it applicable to different systems that over time get also increasingly complicated. And what we hope to understand, and to which I'm trying to contribute a little bit today, is sort of two facets of that history and its philosophical significance. On the one hand side, the conceptual change in itself, so just trying to pin down more precisely how the concept of equilibrium has changed from one application to another as it's been extended throughout the history of physics, and how those different instances are related historically and conceptually, but also, and perhaps more importantly, identify common threads of methodological continuity to figure out whether there are some common sets of inferences that equilibrium reasoning, the use of the equilibrium concepts in the different cases in the history of physics, generally tends to underwrite. And maybe that can explain how it is extended from one case to another. So what are the driving desiderata that equilibrium reasoning addresses? And the very basic idea there is that I think equilibrium is often used as a specific kind of idealization, an idealization that licenses counterfactual inferences about causes of disequilibria, right? So we model a system to be in a state of equilibrium, because then, given the theory of the balance properties and the balancing relations, we can draw counterfactual inferences about what might explain disequilibria when such disequilibria occur. Thereby, we can reveal then some counterfactual dependencies in the physical world, hopefully. Okay. But today, this is all generic and abstract and hand-wavy. I want to look at one specific episode in the conceptual history of equilibrium, as I said, and that centers on Newton's Principia. The Newton's Principia generalized the notions of static equilibrium that inherited from Galileo and the ancients, as we learned, and that allowed him to characterize balanced systems of various types in terms of forces, Newtonian forces, and devise idealizations that treat systems to be in balance under Newtonian forces for a large array of new systems that couldn't be described in this way before. The generality of Newtonian mechanics, the theory that describes the balance properties, then allowed him to draw much more powerful counterfactual inferences that link various types of disequilibria or perturbations to unaccounted forces and masses. So if equilibrium in some sense always is about counterfactual reasoning, that counterfactual reasoning became much more powerful in Newtonian mechanics. And I'll try to argue that those inferences underride what George Smith has called the methodology of Newtonian idealization, or if you like, de-idealization. That is actually characteristic of the Principia and later work in celestial mechanics and geophysics up to the present day. So put these things together. Okay, the plan is as follows. I'm going to talk a little bit briefly, schematically, and hand-wavily about equilibrium and static reasoning before the Principia. I'm hoping that Sarah doesn't look too closely at what I'm saying. Then I'm going to talk about equilibrium in the Principia, try to understand how the concept changes in the context of Newtonian mechanics, and then look at how it's used in inference in the methodology of the Principia and celestial mechanics research afterwards. There will be two really natural case studies. One is about orbits. The other one is about the shape of planets, the two great problems of celestial mechanics. Since I think we should all look at the second one because we haven't looked at it enough, and I'm writing a book about it, I'm going to look at that case study, which is the modeling of the equilibrium figures of rotating self-gravitating spheroids, which is just to say the shape of planets, the primary one being the Earth. And then I'm going to try to draw some cautious generalizations about what the specific episode about Newtonian equilibrium idealization tells us perhaps about the use of equilibrium reasoning in physics more broadly. Okay, let's start. So for a large part of the history of mechanics, like maybe leaving aside Aristotle and Plato, the main principle by which equilibrium has been operationalized is the law of the balance or lever, which, and this is a quote from the standard translation that we already heard, according to which commensurate magnitude incline equally, hence are in equilibrium, when they have the same ratio for the length inversely as their weights. You can, of course, describe the simple fulcrum balance with that, but also, more complicated versions where you substitute individual weights by further balances and so on and so forth. So you can use it to measure weights and distances in virtue of each other, and you can draw some counterfactual inferences about whether a change in weight or a change in the construction of a specific device leads to a disequilibrium. It perturbs equilibrium. However, the scope of such counterfactual inferences is very limited because it's not really clear what equilibrium means outside of a device, since it is defined in terms of distances within such a device and weights that are connected to it, right? And so it's very limited in its applicability. You can see already with the so-called neo-Archimedeans, as Palmieri calls them, in the early modern age, attempts to extend the scope of equilibrium before statics in this more narrow sense. In some sense, you already see it in the ancients, but very explicitly with people like Galileo, Viviani, Torricelli, who attempt to extend equilibrium reasoning expressly beyond machines and statics, and use equilibrium as an idealization to solve problems that are not about statics, but really about kinematics, problems about motion. Right? So think, for example, about Galileo's use of the principle of the balance in his theory of or description of the inclined plane, or like in the various further applications of that, where what we're doing is we're interested in what happens to the body A on the inclined plane if the weight P that balances it, holds it in equilibrium, were to be removed, right? It tells us something about the instantaneous velocity that the body would have depending on the height it has relative to the ground and its position on the inclined plane. So we can use it to solve problems of motion. So for example, famously, we can look at how the angle of inclination affects the instantaneous velocity, and eventually, of course, the change in the instantaneous velocity, the constant acceleration, independently of the path that the body takes. Of course, Galileo introduces this new quantity, the impetus, which is closely related to what Newton comes to call the quantity of motion, the product of the weight, or we would now say the mass, and the velocity, using exactly that kind of thought experiment. The key point is, we're interested now in counterfactual inferences about kinematics, about motions, not just strictly about statics. There are some common features of all of these applications, even the kinematic ones. The stationarity, the stationarity that we require for equilibrium is generally accessible empirically to us, right? We can look at a system and see whether there is equilibrium or not, whether the balance moves or not, whether the ball rolls down the inclined plane, et cetera, et cetera. And then we can infer rules for how or whether that equilibrium is preserved. The principles of equilibrium in these cases are applicable, usually strictly to mechanical devices, and the properties in virtue of which the equilibrium is maintained is generally tied to the physical properties of such devices, such as the length of the fulcrum or the weights hanging from a pulley and so on and so forth. And that is in some sense true even of Galileo's impetus and instantaneous velocity, because the inclined plane is used in the pendulum, because given the complexity of air resistance, we can't really study it outside of those contexts. And Galileo doesn't make a great effort of trying to recover the motion under such complicated circumstances. But as I also showed you, there is already like an attempt to extend equilibrium beyond statics and beyond the applicability to such machines, which is the case of Galileo and Torricelli suggests, is motivated by the power of equilibrium reasoning to license counterfactual inferences about causes of disequilibria, in this case, purely kinematic causes. Right? So we don't have forces here that explain the kinematics. We're only talking about using statics as an idealization to make inferences about motion, not about the causes of motion in terms of forces. That changes quite drastically in Newton's Principia. And in fact, Newton is very explicitly about this aspect already in the preface to the reader of the first edition. And changes in two ways. First, Newtonian mechanics is mechanics of forces, first and foremost, not just about kinematics. And second, it is, in virtue of being about forces in a very generic sense, not limited to manual devices. It doesn't require pulleys and doesn't require fulcrum arms to reason about statics and kinematics. So Newton says, rational mechanics will be the science expressed in exact propositions and demonstrations of the motions that result from any forces whatever, and of the forces that are required for any motion whatever. The ancients studied this part of mechanics in terms of the 5 powers, the 5 machines, right? But since we're concerned with natural philosophy rather than manual art, and are writing about natural rather than manual powers, we concentrate on aspects of various kinds of forces: gravity, levity, elastic forces, resistance of fluids, forces of this, all these sorts, Newton says, and whether these forces are attractive or impulsive. Okay? So you see the extension beyond the manual machines, the mechanical impressed forces, and you can see physics really focused fundamentally in his language on forces. This shows up in 2 ways. And the first way it shows up is that Newton's Principia is about forces. So when we do kinematics and statics, we're really interested in how those kinematics and statics measure underlying forces, right? As Principia is full of examples. The famous one is, of course, that when you consider centripetal forces, like details about the orbits, such as the ratio of the periods and radii of different satellites that are within moving around the same, partaking in centripetal motion around the same center, the ratio of those measures the exponent of the force law characterizing how gravity or any centripetal force varies distance to the center, right? Which famously is used by Newton in his argument for universal gravity. More simply, when we use a pendulum, right, we infer, or we use the kinematic behavior of the pendulum to measure the force of gravity that underlies it, right? In this case, the mass of an attracted body. But these forces, Newton's Principia is not only about forces, but what we mean by force is much more general than what has been meant by force or analogous concepts like impetus prior to the Principia. It exceeds those more mechanical accounts in generality and inferential scope. There's all sorts of new things that you can do with forces in the Principia that you couldn't quite do before. You can add them using vector addition. You can scale, like you can not just add them using the parallelogram, but more interestingly, you can add up the component forces of parts of a body to the resultant force exerted by the body in the case of attractive forces like gravity. And those forces can act attractively and repulsively without any immediately apparent medium or mechanism that transfers those forces, such is the case in the machines. Think about orbits, for example, orbits under gravity. Famously, that is not the case. Hence, methodologically speaking, we can now detect, measure, and study forces independently of the specific mechanical devices or contact actions or identifiable sources of those forces. In fact, we can use the forces to make inferences about, say, the masses that generate them in the case of the orbits. Okay? And as a result, of course, this kind of thinking about forces and mechanics suggests a much broader understanding of what equilibrium is. In a very simple sense, it's a net zero of forces that act in any manner, like all the different kinds of forces we discussed, and in any direction whatsoever, very generically. And more importantly, thinking more about its application in actual empirical problem solving, we can then pin down more specific equilibrium principles to describe, to model a much greater class of systems. Two systems are historically incredibly important, and we're going to discuss one in great detail. Think, for example, the equilibrium of orbital motion under centrifugal forces, right? It's a dynamical equilibrium. We don't look up at the sky and like think, oh, this is a stationary system. But we can see if we add up the tendency of inertia and the gravity towards the center over time, that they balance out over the course of the orbit. So we can treat orbits as equilibrium over under the action of a force that acts over distance without any pulley or lever in a way that would not have been intelligible really before Newtonian mechanics. Similarly, it's the case with the equilibrium shapes of bodies. When they start rotating, say in the case of the Earth that we're going to talk about in great detail, we can think about what it would take for that body under the action of the gravity of gravitation of all its parts and the rotation around its rotational axis for the shape of that body to remain in equilibrium. Again, it's an application of equilibrium that wouldn't have been really intelligible before the generality of Newtonian mechanics and the additivity of particle forces to composite forces. Okay, so there's a bunch of changes that occur to Newton's mechanics, right? Just to summarize, equilibrium is no longer operationalized by the balanced lever or like equivalent machines, but it is, you can understand it very generically as the balance of Newtonian forces of various kinds. Equilibrium in the process obtains a much richer theoretical meaning. It is no longer determined exclusively by direct observation of stationarity. You can make inferences about a system being stationary in a respect that are dictated by theory that are not immediately apparent to you, such as orbits. And it can even apply to systems. Oh yeah, this is what I just said. Okay. It can also be further specified in the way I just described to apply to a vast array of new systems that weren't subject to equilibrium reasoning in the same way, at least not in a productive, empirically successful way before, and that are not mechanical devices in the customary sense. And this is the point to which we're working towards. The generality of the mechanics then allows for much more powerful counterfactual inferences that you can already see latent in the work, say, of Galileo and Torricelli, but the causes of disequilibria, right? And reason why equilibrium does not obtain. And these two parts, the specification of the equilibrium principles and the use of equilibrium reasoning in counterfactual reasoning in Newtonian mechanics, is what I'll try to explore historically, show you the power of this method and its application throughout the remainder of the talk. Okay. And the method in which these equilibrium principles are applied in the concept of Principia is what George Smith has described in what I think is the best reading of Newton's method we have available as the method of Newtonian idealization. In that method, you start by deriving predictions from some theory for idealized models of a target phenomenon, such as two-body orbital systems. You compare those predictions with measurements and identify systematic discrepancies, and then you gradually refine those idealized models to identify robust sources for all those discrepancies, which in the long run allow for increasingly stable, convergent, and precise measurements of the parameters of your theory. Okay. What matters for us that in practice, if not in principle, what those systematic discrepancies are in Newtonian mechanics, they're modeled generally as perturbations of an equilibrium state, such as the two-body equilibrium, two-body orbit equilibrium, or the equilibrium shape of the Earth, as we're going to discuss. And my contention here is that we can understand Newtonian idealization as a uniquely powerful form of this broader tendency of draw counterfactual inference from equilibrium reasoning that you can already see latent in the mechanics before, but that requires a theory of the power and generality of Newtonian mechanics to be applied successfully. Okay, let's look in detail at how this plays out, how it is applied to my favorite example anywhere, right? Newton's Principia is concerned, a very important problem in Newton's Principia is determining the shape of the Earth, right? Why is that so important? Because Newton desperately needs evidence for the most novel principle of his theory, and perhaps the most controversial, the idea that you can get the attraction of a composite body, the gravitational attraction, by adding up the attraction of its parts, by integrating, as you can see here, right? That is a very novel assumption that most of Newton's contemporaries, such as Christian Huygens, are not ready to accept. Huygens says he's not in agreement with Newton's principle that all the small parts that we can imagine in two or more bodies attract one another or tend to attract each other mutually. He couldn't concede it. Neither was he convinced that the third law of motion applies to gravity. So Newton had a problem. He had to produce an empirical prediction that constitutively depended on the parts of celestial bodies, not just the celestial bodies considered as spheres or point masses, to make a difference to empirical measurement. The problem was that for all cases in astronomy, alternative theories of gravity that didn't commit to that assumptions were empirically equivalent to Newton's theory, right? So if you think about centripetal forces, right, like that you use to determine orbits, all that matters is how gravity varies as a function of distance to the center around which the motion tends. But there are alternative theories, such as the ones endorsed by Huygens, where you simply say that is what gravity is, right? All we can say about gravity is this is a certain way in which gravity varies as a function of distance, and maybe you can characterize that mechanically. If you apply that to the attraction of composite bodies, Newton himself shows it gives you, if they're spherical, it gives you equivalent predictions for the attraction outside of that body as Newton's theory. Because if you integrate to get the attraction of a sphere, you could always substitute it by having the attraction of a point in the middle of the sphere that has a greater mass. So the variation of gravity outside of spheres is the same. It is not the case, however, when you look at non-spherical bodies, spheroidal bodies, right? Where the Newtonian theory gives you a different prediction. So think, for example, about an oblate spheroid, such as the Earth, that's squashed at the poles, right? If you're at the poles on the standard theory, where you just take the centripetal, the variation of gravity with distance, all that should matter for the attraction at the pole is your distance to the center, that is that axis, right? But of course, there's extra mass to the side, right? If it's squashed. So on the Newtonian theory, where gravitation is produced by adding up the attractions of all the parts of mass, of matter, that should make a difference. So on the Newtonian theory, when you integrate to get the attraction, you get a different attraction at the pole, and you get a different variation of gravity on the surface of such a non-spherical figure. To then test the prediction for but to derive predictions for how gravity varies on the surface of non-spheroidal bodies of equilibrium, such as the Earth, Newton first needs a principle that applies equilibrium to such cases, right? He wants to have the variation of gravity on the surface of the Earth imagined as a body of equilibrium. You first have to figure out what the figure is of the Earth. So Newton comes up with a new definition of what it means for a rotating body whose parts attract each other mutually according to some law to be in a state of hydrostatic equilibrium. It's pretty stipulative. He says, well, imagine two columns of water, right, connecting the pole and the equator of a body, the spheroid, to its center. Now imagine the spheroid starts rotating, right? We can say that that body is in hydrostatic equilibrium if the net force weight on those two canals is exactly the same. Since it's rotating, the equatorial canal has to be extended. That is, the figure has to be squashed at the poles. And that ratio, the ratio between the length of the polar axis and the equatorial axis, or the semi-axis and the semi-diameter, that becomes a really important problem to predict, to test Newton's theory of gravity, because it directly depends on whether the parts of the Earth attract, that is, whether you calculate the attractions within that body using integration or just the simple variation of distance that Newton's contemporaries believe. So it's a crucial experiment for Newton's theory. So he derives two predictions for the test measurable parameters that depend on that assumption. One is simply the equilibrium figure itself. He calculates how much the Earth has to be flattened, what its ellipticity has to be, such that it satisfies those equilibrium conditions. He corrects that several times throughout the different editions of the Principia, but you can disregard it. I took the slide from an older presentation. A corresponding variation in the length of 1 degree of a meridian, right? So if you imagine the Earth is squashed at the poles, then as you move from the equator to the poles, the section of 1 degree of a meridian will get increasingly long, given the changes in curvature. Similarly, you can then predict the gravity on the surface of such a body, also as a function of latitude. As you go up from the equator to the pole, gravity is supposed to be stronger, it's supposed to vary. And that variation depends on the law that characterizes the attraction of the parts of the body. So Newton predicts two things. He predicts the overall ellipticity, and he predicts the variation of gravity with latitude on the surface of that body, of the Earth. You can measure those things already with contemporary devices. You can measure the variation of gravity with a pendulum clock, and you can use this procedure called triangulation. It's just a sophisticated way of measuring distance to compare the length that 1 degree of a meridian has at different latitudes. And this is what people start doing. I'm not really going to talk about this today to focus on the topic and save some time. Okay. The problem is for Newton, this is just his revisions of his predictions as he prepares the third edition. The data doesn't really work out. He has all sorts of explanation why that is the case and not really convincing. the variation of gravity with latitude that is actually measured by contemporaries doesn't seem to agree with his predictions based on his hydrostatic equilibrium model of the Earth and its attraction. And a key reason for that is that the Earth is not uniformly dense, but Newton's theory only applies to the and his principle only applies to the hydrostatic equilibrium of uniformly dense rotating bodies. Okay, so the thing that you need to do in the spirit of the program of Newtonian de-idealization or idealization, I didn't remove the de-idealization on that slide. Right, so you do the Newtonian idealizations and de-idealize and understand the causes of perturbation. Is to extend that to find a principle of hydrostatic equilibrium that applies to a non-uniformly dense Earth. And Alexis Clairaut, the great French physicist, shows in 73 that Newton's principle of the canals, once you have different layers of density within the body, is not necessary, neither necessary nor sufficient to derive the hydrostatic equilibrium for such a complicated body. So you need a more complicated, more advanced understanding of hydrostatic equilibrium, which takes into account the individual and composite shapes and attractions of all the different layers within a body. And Clairaut develops such a generalized equilibrium principle, which in essence is still the one that we use today, according to which you don't have those two canals, but you have arbitrarily shaped canals that connect any points on the surface of the body, or they're enclosing themselves. And then the forces along those canals have to cancel. And only if all those forces cancel, that is, another way of putting it, if the surfaces of equal potential and the surfaces of equal pressure and the surfaces of equal density coincide, then you can say of such a body that is in hydrostatic equilibrium under rotation, under the action of gravitation. So he comes up with a new specification of hydrostatic equilibrium to handle those more complicated systems. And he derives a prediction for the ellipticity and variation of surface gravity for such more complicated rotating bodies. On Clairaut's theory, the ellipticity is no longer a unique value as per Newton, but it's bound within an interval of values. And this is Clairaut's famous theorem that characterizes how gravity varies as a function of latitude, effective gravity. So m is just an empirical parameter, that is the ratio of centrifugal force to gravity at the equator. E is the ellipticity that we're trying to determine, and sine squared, just as in Newton's case, gives you the elliptic shape of that surface. Okay. So the question becomes, can we show that if Newton's narrow prediction for the ellipticity doesn't agree with the measured variations in gravity, maybe that generalized interval that Clairaut derives using a more advanced equilibrium principle, that can account for the measured data. That is, the variation of density inside of the Earth is the source of the perturbation that explains the failure of the previous model. And Laplace, in the end of the 18th century, gives us some good evidence for that. He shows that taking 15 measurements, that you get a somewhat unique value that's implied by the best fit to those measurements, the red here being the best fit and the green being the raw measurement data, that you can get a unique value that falls within the interval. So the Earth's ellipticity is somewhat smaller than Newton had assumed, which is due to the increasing density within the Earth. So you have an explanation of the previous discrepancies from the model of the Earth hydrostatic equilibrium shape in terms of the gravitational attraction of the internal layers within the Earth. But even that equilibrium model, the perfect ellipsoid, that one has further, even with the variable density, turns out to reveal further anomalies when applied to more measurements. This is by the 1830s, work by George Airy, where we have already 63 different measurements of gravity at different latitudes. Before, Laplace had 15. And you can see very clearly that there are notable outliers, especially here up at 63 degrees latitude, and then closer at lower latitude. And the question becomes again, okay, why is it that if the Earth is a Newtonian self-gravitating rotating spheroids in hydrostatic equilibrium, that there are those anomalies, those discrepancies from what the surface ought to be according to theory? And over the next decades, towards the end of the 19th century, we get some sort of satisfactory explanation. The causes of those remaining anomalies in the variation of gravity with latitude are attributed to a process that's called isostatic compensation. So there are those compensation processes going on where surpluses in the Earth's topography and deficits of mass and deficits of mass below the Earth's surface are compensated, right? So imagine you have a big mountain range like the Himalayas. They're very massive. Then below the Himalayas, which is actually the case, there is in the mantle of the Earth, below the crust, is a deficit of density. So overall, the Earth's surface in this region still maintains equilibrium, right? So if you take this into account, you can explain why there were those apparent variations of equilibrium. So you de-idealize the model further, taking account those geologic processes of isostatic compensation. But, and just to hammer home that this is really, up until the very end, an idealization, even isostatic compensation we learned in the middle of the 20th century is insufficient to account for all gravity. This is the report on the result of the Vanguard satellite measurement of gravity. It's the first artificial satellite that is used to measure to map out the Earth's gravitational field. And the Vanguard satellite mission shows us that there are further anomalies, if you take into account higher order terms in the Earth's gravitational potential, in the equilibrium, in the surface of the Earth, that violate hydrostatic equilibrium entirely, right? So if you think first order model is the sphere, second order model is the ellipsoid, third order model is like a pear-shaped figure. By taking into account the attraction of those parts of the Earth, they show that there's anomalies in gravity that are incompatible with the hydrostatic equilibrium of the fluid. So the Earth is in fact not in hydrostatic equilibrium, and what geodesists then called the basic hypothesis of geodesy, going back all the way to Newton, that the Earth is a rotating sphere in hydrostatic equilibrium, is strictly speaking false, right? But notice that we're talking here about variations in gravity that are 2 orders magnitude higher, finer, more precise than the ones that we were considering back in the day of Newton. So while this equilibrium idealization turns out to be false, it revealed a lot of interesting counterfactual dependencies between what the equilibrium surface of the Earth would be and the actual physical composition of the Earth. Discovered that Earth's density increases inwardly. We have discovered that there's these processes of isostatic compensation going on, which is the foundation of our modern theory of continental drift. And we are able to measure the Earth gravitational field of a precision that is at least 2 orders of magnitude greater than what we started with, right? So while the model turns out false, it revealed a lot of interesting counterfactual dependencies and a myriad of physical details about the Earth that explain those counterfactual dependencies. Is an application of this method of Newtonian idealization. Okay, so what can we learn about equilibrium reasoning from this whole story? My contention is, if we think about equilibrium idealization as a broader practice, we can think about the application in Newtonian idealization as a special case, right? So think about equilibrium idealization as the practice of treating a system as being in some state of equilibrium, to draw counterfactual inferences about perturbations of that state in virtue of a theory that characterizes the balance properties. As we said already, Galileo shows that such counterfactual inferences can be extended from statics to kinematics, and then we can draw some limited inferences about motion under violation of equilibrium. But with the generality of a properly dynamic physics, as is it Newtonian mechanics offers us, we can radically increase the scope of such inferences. We can characterize a whole lot of new systems as being in a state of equilibrium and identify physical sources for perturbations of such equilibrium states, such that I think we can understand Newtonian idealization as a specific kind of equilibrium idealization, and that illustrates a broader way in which we in physics use equilibrium reasoning to reveal physical details about systems that we study. And the value of such idealizations, I think, lies in the increasingly strong counterfactual dependencies it reveals as we gradually de-idealize the equilibrium models at our disposal. It's rather than the literal truth, right? As you saw in the case that we looked at, the Earth, of course, is not in perfect hydrostatic equilibrium. It's not perfectly balanced. It's still kind of moving around, but by assuming it across a sequence of increasingly fine-grained models, we have revealed a lot of robustly, independently interesting and well-verified details about what the actual physical Earth is. Okay. Another interesting perspective perhaps is on conceptual change and the further specification of the concept of equilibrium along the way, right? What happened in this case is that to properly apply counterfactual reasoning over time to understand the increasing details and the resulting perturbations of the Earth, the physical Earth, we needed to define more sharply and extend our concept of equilibrium. So the specific physical principles that we use to apply equilibrium reasoning to different systems seem to be responsive to the complexity and domain specificity of the systems that we study, and that changes to those concepts are driven by being responsive to those details. So think, for example, if you go all the way back, the balance lever, it's applicable to small class of mechanical devices. Then in the case that we looked at, in the framework of Newtonian mechanics with the principle of canals, we can already apply it to homogeneous rotating self-gravitating spheroids, because then we found out the Earth is not such homogeneous spheroid, right? It has varying densities. So, but to even describe the equilibrium of such variably dense bodies, we then need a further generalized specification of what equilibrium is that we get from Clairaut, which is in a more modern language of partial differential equations, still our concept of equilibrium in classical mechanics for rotating bodies under gravity today. So we can apply the principle of equilibrium also to rotating bodies that are not uniformly dense, right? So to reason about the physical composition of those different systems that get increasingly complicated, we have to further specify what we mean by equilibrium, the criteria, the conditions for different systems to be in equilibrium, more fine-grained and extensive ways. So the methodology here of equilibrium idealization, in this specific case, Newtonian idealization, drives the conceptual change of the equilibrium concept. Okay, to wrap up, some conclusions. I tried to discuss how Newton's Principia transformed our concept of equilibrium from mostly static and observational concept into one that's characterized in terms of a more general theory, a theory that is a dynamical theory. It speaks in terms of forces, further analyzes causes of motion, not just motions themselves, and thereby making the concept of equilibrium broadly applicable to a variety of physically interesting systems to which we couldn't apply it before in a fruitful way. This broader applicability and the new rich theoretical content of equilibrium within the framework of Newtonian mechanics allowed for new equilibrium principles, new idealized models of equilibrium systems, and then in virtue of that, new powerful counterfactual inferences about the causes of perturbations of equilibrium, which we demonstrated for the case of the Earth, where those causes of perturbations were increasing physical details in the composition of the Earth that we could account for, that explained why the Earth deviates from a simpler equilibrium model in a specific way, such that we can understand the characteristic method of the Principia and celestial mechanics afterwards, Newtonian idealization, as a particular form perhaps of this general tendency of equilibrium idealization in reasoning and science, where we draw counterfactual inferences about causes of disequilibria by treating a system being in equilibrium. In this case, owing its power, its wide applicability to the power and generality of Newtonian mechanics. And then I made a claim about what the value of equilibrium idealization, at least in this case, really is. It's not about the literal truth. We're not depending on eventually finding an equilibrium model of the system, but in the process of gradually building more sophisticated equilibrium models and explaining their perturbations, we reveal counterfactual dependencies in the physical world that are independently interesting, independently of the literal truth of the equilibrium models that we construct. Okay, that's it for me. Thank you.
Hello. Miguel, thank you very much for this interesting talk. The concept of stationary state trigger me a lot of thoughts. So let's see if I can articulate a question. A stationary state is connected to a state where all the forces on it are in equilibrium, so they are canceled out each other. So we can also imagine with a body with no forces on it, and the equilibrium is broke when some other forces is on it. But the idealization of force to get that for me is evident when you switch to the biological systems, when you have an opposite logic. You have a lot of proteins and enzymes to try to keep an equilibrium. So in terms of thermodynamical terms, you have a lot of energy in terms of enthalpy to contrast the entropy typical of the system. So I wonder what's the difference in a physical systems that's made that entropy of the world, like, doesn't rule it out. So I tend to think that the key point there is the principle of inertia, or the impetus from Galileo, as you say. But I want to see what way you think about it. But
Yeah. Let me see if I understand correctly, right? So why is it that in those applications of mechanics we can disregard entropy, while in the biological cases we can't? Instead, the thermodynamical entropy. Well, I'm not sure I have a satisfactory answer, because the answer to me seems to be sort of a physical answer. It's just that here we're studying systems where the thermal effects are negligible, right? And the effects of entropy are negligible. That is why I mean, this is not true for all of geophysics, right? At some point, if you would carry those idealizations further, you would get thermal effects that those drive plate tectonics. Those eventually explain why you have isostatic compensation. So even when we model like physical systems like the Earth, at some point you get thermal phenomena, and you might want to think about entropy. But it's just that, like, this is a branch of classical mechanics where, for the purposes of the precision of the predictions and modeling that we're interested in, you can disregard entropy, while in other kinds of systems you can't, right? But nothing. I'm not sure that anything in the methodology that I'm interested in here sort of guaranteed that this is the case, right? So if you then think about the application of equilibrium and studying deviations from equilibrium and non-equilibrium thermodynamics, it's sort of a further history in that, like a further step in the concept, in that broader conceptual history. And it's an independently interesting question how then the mechanical equilibrium in terms of forces or potential energy, etc., relates to the thermodynamic equilibrium, how it historically related, which is something we're independently interested in. But I'm not sure, like, based on this material, I have a good answer, other than simply saying, well, in these cases, they were lucky that effects of like generally thermodynamic effects and like entropy were not salient enough at the level of description that they were studying, say, the Earth. But you could say the same about orbital motions. You just didn't have to worry about them, such that this notion of equilibrium was sufficient to study it. Yeah.
Oh, okay. Yeah, so another, I guess this is just like a comment, and it's more like, so there's another kind of use of equilibrium that was kind of has a parallel history here, that I just wanted to mention. And I mean, you know about this, but there's Hooke's law, right? Which is a case where there's it's a balance of forces, and then there's an equilibrium point, and then when you move away from it, there's a force that tries to restore it, right? And that kind of has this whole history that there's Hooke's law, but then there's the generalization of it in continuum mechanics, right? Elastodynamics that develops in the 1800s. You can, I think you can, and the whole idea of waves, right? Waves are essentially, they're these things that arise because you've got these systems that when you remove them from equilibrium, they try to go back to equilibrium, and then you get the, sine wave type behavior, right? And so this whole kind of parallel history there. And I was wondering if you had any, I just wanted to actually just point that out, and that there's an interesting, right?
No, it's perfect. Yeah. I mean, this is not exhaustive of the history of equilibrium reasoning in classical mechanics or anywhere else in physics, right? So I'm sure the interesting question will be as to whether, when you look at the extension of Hooke's law, such as like in elastodynamics, whether you could tell a similar story as that you get further specifications using the theory of elastodynamics of Hooke's law applications that are driven by the need to model perturbations, right? Whether you can have I guess Marius Stan would say yes. Yeah, you would say too. Excellent. Yeah. So my sense is like it might be that it's like a very similar. You can tell a very similar story about Newtonian idealization. This is the more straightforward case, right? Because it's gravitation and things are a little bit simpler. Although this is compared to orbital mechanics, this is the more difficult end, right? Because the Earth is kind of tricky. But yeah, so I think logically, I'm inclined to think reading work by you and by Marius, that you could tell a similar story about equilibrium reasoning about, going from Hooke's law to elasticity theory too. And I think it, like it's water on our mills, right? Like it is another case where you have like, you start with the very generic principle of equilibrium. It's also mechanically defined. You get Newtonian mechanics. You can generalize it. You get like, I guess, eventually Lagrangian Hamiltonian mechanics, and you can apply it very, very widely and very productively. But what equilibrium means is extended in the process and made more general, such that you can tell a story of how the conceptual change of equilibrium is driven by a methodology of equilibrium reasoning. In this case, I think a very similar one of Newtonian idealization, just without the theory of gravitation, but the general theory of elastic waves. Yeah, that would be my intuition. Right? If that's true, we have to find out.
Follow-up priority. So I think it follow-up.
Thanks for your talk. So I really enjoyed the connection between equilibrium and the idealization. So especially like the first point. So I wanted to ask, partly through reading George's work as well, there's this, to de-idealize, to identify a source of perturbation. One thing you do is to find an invariant, like kind of a structural concept that's satisfied by like the new theory and the old theory. And then there's a physically meaningful like detail. And then it seems like those at least conceptually come apart. And then so I was wondering when you when you identify these perturbations, are you doing the structural thing or the physical thing? And like at least the structural thing. Can we just do the structural thing?
Okay, let me make sure I understand. I'm not sure I understand the structural physical distinction in this case. Can you? Yeah.
Well, at least I was just thinking that like you're identifying like some sort of invariant variable that like, okay, then I'm identifying this maybe a number, a variable across all of these different like domains of inquiry. And then I'm like, oh, once we get that in, and then and we can like successfully de-idealize, and then I don't have to like give a mechanism, or at least like in the examples here, like I'm looking like in your examples, like we point to like this physical detail in the wall, but like what if we don't do that, and then we just like, oh, there's a variable here, and we plug that in.
Good. Yeah, I think I got it. So there's at least two like salient levels of distinction within your distinction, right? One is like what is it like? Give you one way of like one part of your question is, okay, look, the meaning changes here of hydrostatic equilibrium, right? As we keep on modeling. So what is it that ties the different stages of idealization together? That is like, what's the physical quantities invariantly characterizing both of the levels of description? And that's of course Newtonian gravitation, right? And so part of the story is Newtonian mechanics and Newtonian gravitational mechanics, the sub-branch of it, is powerful enough such that you can characterize the initial model, which is a solution, an equilibrium solution, and like a further description that accounts for the perturbation, right? Sometimes it's exact, sometimes it's not. But yeah, there is this like physical continuity in the overarching theory, and what's invariant is in this case Newton's law and like the laws of mechanics. Another question is that is related to it is, okay, what we tend to do is, what's novel about the Principia is you can talk about forces as forces, right? Yeah, there are mass, like in the case of gravity, there will be a mass corresponding to it, right? But there's no problem of describing how a force acts independently of knowing the mass that is its source, right? And even if we don't have a medium through which it spreads. So you can just give this characterization and you can see whether that is robust, and whether to close the loop, so to speak, you always need to then identify like physical masses that correspond. I'm not sure, like there is I can't really visualize how it would work, since we're interested in physical modeling here, right? Like how we could proceed in accounting for the sources of perturbations without, in the case of gravitational theory, identifying a system of masses or their distribution in density, say in the internal structure of the Earth, to account for it. I can't see that the mathematical and the physical can come apart, since the purpose seems to be to reveal further physical aspects of the system, and those tend to be in terms of things other than forces, right? Masses and densities. I hope that answers the question. I hope I understood it correctly. Yeah.
Okay, hi. Thanks for the talk. This is going to follow up on the previous question, I think. So I was wondering if I could get you to go back some slides to the one where they're talking about the pear shape of,
The pear shape? Oh,
yeah.
Yeah, it's a cool
Yeah,
picture, yeah. Okay.
yes, this one.
Yeah, yeah,
Okay,
okay.
so I understand the claim that the continuity here is of, Newton's laws, but I'm wondering, in the cases in which we're applying these kinds of things, if the basic hypothesis of geodesy, the part that you highlight, is the thing that's being called under question, at what point do we say we're no longer like de-idealizing or closing the loop and we've like switched to another loop or so I understand the continuity part, but it feels like once you zoom into the geodesy part, the continuity is a little bit trickier to establish.
Oh, okay. So I guess like in that would also apply in some shape or form to the previous step, where suddenly you're doing something that looks a bit like geology to explain the perturbations rather than, yeah. I guess like my sense is, here what we're talking about is still the gravitational potential of the Earth, right? And what the basic hypothesis of geodesy is that it's not even the gravity, it's the effective potential. So rotation and gravity together is that the effective gravitational field of the Earth is one that corresponding to a figure of rotational equilibrium, right? That is the basic hypothesis. And for that to be the case, you have to have all those geologic compensations work, and they figure out using the satellite measurements that the Earth is not sufficiently compensated at some level of description that it doesn't work. My sense is, as long as we are, it might be that the models that we're using look like increasingly clumsy, not clumsy, but like clunky, like more details on the side, they reach into geology. If you keep it, as I mentioned before, if you keep going further, you want to understand the sources of those compensations, you have to apply like thermal physics to the internal structure of the Earth, which drives the compensation mechanisms. So it sort of branches out. My sense is, as long as there is no sense of like theoretical inconsistency between what we use to characterize the perturbation and what you initially use to derive the idealization, I don't think there's a problem for this kind of methodology. I understand it in this very general way. There's a section in Closing the Loop where this is discussed. And like George Smith comes down on like a similar view. Like it could have been Newton's, it's about the question of whether the success of Newton's law in astronomy depended on there basically only being gravitational forces active in the solar system. What if there were other kinds of forces? Well, that wouldn't, so you can understand the methodology in a more general and a less general way. The less general way is just gravitational, but there's an important structure feature of the methodology that evidently carries over to the more general case, where you use different theories to characterize the perturbations, as long as those are not inconsistent. The really interesting case is then the transition from Newtonian gravitation to GR. And there the key, then the interesting question becomes, what are the right kind of limiting relations such that you can speak about this method of perturbation modeling carrying over from one theory to the other? Newton, in fact, does the very same thing in relationship to Galilean mechanics, right? Why did Galileo get the pendulum right, even though the gravitational field of the Earth is it's like at least spherical or ellipsoidal, and he treats gravity as constant. And he shows, well, if the radius is sufficiently large, then it's exactly what my theory would also predict. And he needs to do it such that there is some kind of evidential transfer from one to the other. So that is the trickiest case is there where you really have an inconsistency between the theories considered by themselves. But if you can then conceptually, if you can spell out a limiting case relationship, as often happens in the history of physics, I would say that even in those cases, you can speak of like continuity in the method across theory change, such that you can have a very general understanding of this kind of idealizational methods that's very powerful and bridges some of the worries about incommensurability and so on and so forth. Yeah, I hope that's an answer. Excellent.
May I ask a question about the conceptual change of like notion of equilibrium?
Yeah.
I think it would be interesting to talk about like different variants of like equilibrium, because like according to the perturbation that's attached to the equilibrium, you might have like unstable equilibrium, which means like once perturbed, even very small perturbation could leave it away, all the way away from the equilibrium state. Or you have stable equilibrium in the sense like you have a range of perturbations under which will go back, like even it's perturbed from away from the equilibrium state, go back to the equilibrium state, which is very relevant to thermodynamics. And also you have some sort of like dynamical equilibrium in which like the perturbation will just periodically like perturb the systems back and forth.
Yeah.
So there could be like different variants of notion of equilibrium. Maybe it's relevant. There's a like conceptual history about them, but like I would be super interested in knowing more about how those notions, different variants are connected to like Principia or Principia
Yeah, yeah.
history.
So specifically, stable and unstable equilibrium, right? Is the question. Yeah. So that's very interesting. It's it fits in this history too. So the idea of a state, like studying the stability of hydrostatic equilibrium figures under rotation, is very, very, I mean, by my standards, very, very young. So it's like a late 19th century thing. And it's now very important in astrophysics, right?
Yeah.
It becomes important when you want to understand not just you want to check whether, here's a planet, here's some parameters about its gravity and its like geometry. Is it in a state of equilibrium? And then you can discover further details. But you want to understand how that planet evolved over time, right? And for that, you really need to understand how stable the equilibrium is. So my understanding is that you can tell a parallel story of a further specification of the equilibrium concept. In this case, I don't know the details of the history, maybe Eugene or Wayne, how it happens with the like considerations of stability of thermodynamic equilibrium in the development of that theory. But in this case, like in the late 19th century, that becomes the thing once you think about stellar and like evolution, the age of the Earth, like all these questions sort of arise at the same time. And then like you can use the same kind of models, but you can think about the equilibriums as being more or less stable. So in some sense, it's a further specification of what we mean by equilibrium, such that it's applied to diachronic systems undergoing diachronic change, right? Where this becomes a subclass of those kind of systems that are stable, and other might not be. Is that an answer? I don't know.
Yeah. No, it's just more like a comment than a question. And the other one, so yeah.
This is purely a terminological point, but it's something I feel strongly about. One of my undergraduate texts as an undergraduate physics student made a distinction between two kinds of stationary states, unstable and stable stationary states, and only the stable stationary states are equilibria. So for me, talking about unstable equilibria just sounds wrong. And actually, I think that this is a terminological distinction that would give us it would do well to adopt. There are stationary states, some of which are equilibria and some aren't, and the equilibria ones that are stable under small perturbations.
Okay. So, but it's not is that a general understanding? I see people, at least in this history, they do talk about they do take okay. Okay, understood. So like the distinction is between like perturbed equilibrium and unstable equilibrium, and we want to stick with the former rather than the latter. Yeah.
That's a stationary state. Yeah. In fact, it was particular because it was the distinction I guess we're calling this textbook was in connection with the conical pendulum. Big point straight up that is a state at zero, but it's not equilibrium. Equilibrium is big flaw.
I was wondering if there's a connection between the remarks that you're making here and thinking about models as themselves measuring instruments. And in particular, you've got a story over time about how your measuring instrument is changing over time, right? And it seems like as the measuring instrument is changing over time, how you characterize your phenomena is changing over time too. Things that were perturbations or disequilibrium effects become equilibrium or articulable within equilibrium systems. But it seems like, yeah, you've got like this really nice story about like your measuring instrument is this model, is this equilibrium model. Does that sound something like you'd be sympathetic with?
Yeah, I'm sympathetic. It depends on like how picky you are about what you mean by measurement, right?
Right.
You can say, the only thing we're measuring here is gravity and maybe distances, and then we build models with, but I think that's like contrary to practice, and like I don't see any good principle distinction there between those different cases. So I'm open to say, like we're doing a model or theorem mediated measurement. of the say ellipticity of the Earth or parameters of its gravity field or something like that, or its internal density, and then under that in that understanding, the theoretical assumptions are a constitutive part of the model. So you have a changing measure that changes mostly due to changes in our understanding of the measurantes, right? Because in the beginning we take ourselves to measure the ellipticity of a homogeneous spheroid in equilibrium. Well, it's not that, right? So to actually measure the Earth, we'll have to adapt our measurement instrument. Yeah, I'm open to that. I think it's a nice story, and it's fundamentally about theory-mediated measurement. So I agree.
I mean, if we have nothing better to do, then I'll ask a question. And I wanted to press you on the Newtonian de-idealization. So, because I fully understand the Newtonian idealization bit, that's fine. But then sometimes you are using the phrase Newtonian de-idealization, ascribing it to people who kind of worked 15 years after Newton. And I can understand this in like two major ways. One is, oh, it's just the idealization of Newtonian mechanics.
Yeah. But
the other kind of like more kind of in line with what Newton did would be, oh, like what's Newtonian about it is that they take the notion of equilibrium, rewrite it, and smuggle things in that way. And that, but that's, yeah.
What do you mean by smuggling?
I mean, it's sort of like, you know, really, it's like in Clairvaux, for instance, it's the newly introduced concept of equilibrium that whose relation to the previous one is not maybe immediately apparent. That there's a lot of kind of lifting on the argumentation. So this is what I meant by smuggling.
Oh, okay. Yeah, it's what Eugene will call a conceptual anchor, I think. Oh, because
I can also imagine that someone would tell me, oh no, like actually if the situation is a bit more simple, then Clairvaug's equilibrium reduces to the Newtonian one.
It does.
Really generalization of the concept. So maybe smuggling is like not the most, but
no,
yeah,
but
like
right.
Is this what you would call a Newtonian idealization, or is this like a term that you just want to distance yourself?
I realized I had this whole thing done, and then it was all framed in terms of Newtonian de-idealization to highlight that what we're interested in this particular talk is not how do we get the initial idealization, but then how do we apply it in successive steps more fine-grainedly to the actual physical Earth. But then I realized, oh my God, there will be so much terminological confusion. This is already incredibly dense. So let's just cut it out and stick with George's notion of Newtonian idealization. But I didn't delete it on all slides. But anyway, I can still answer your question because it's a substantial question, right? So I like in any way, in any understanding, de-idealization is the point of introducing a Newtonian idealization, right? You get an exact solution, you find discrepancies, and then you add further physical details of the model in virtue of your general theory to account for those perturbations in some robust way. And what I mean by what I would have meant if it was still there by Newtonian de-idealization is not the process of say like further developing the mathematical apparatus of Newtonian mechanics, right? Such that it applies to those increasingly complicated systems. We change the mathematics, introduce partial differential equations, all that stuff. But rather, what I mean is the process of using perhaps often those new mathematical and conceptual tools to develop more physically detailed models of the systems that we're studying to account for discrepancies from the previous model. So it's the method that I mean by Newtonian de-idealization, rather than the development of the theory that is required such that the method applies. And the interesting thing about the case is, well, you can see how the two relate, right? Like you can see how the conceptual and mathematical developments are driven by the ability to account for those increasingly complicated types of perturbations. So the conceptual change is tied to like a methodological continuity. Yeah.
Yeah, thanks. I was thinking on the beginning part, the one where you trace the genealogy from the concept of equilibrium of forces to this kind of Newtonian idealization process. So I was thinking that there is, of course, like another strand of research in physics at the time that is not concerned with forces, but is the one that will lead to like energy conservation considerations, where you have, for instance, the reflection of Da Vinci about the impossibility of building a perpetuum engine, right? And in this case, it seems that the kind of equilibrium used goes in the opposite direction of the one traced here. So the equilibrium state is not something through successive iterations we want to recover, but instead what we want to study is precisely the perturbation themselves. So in a sense, you go away from the equilibrium. So do you think that this kind of Newtonian reasoning exhausts, in a sense, largely equilibrium reasoning, or an opposite direction is feasible?
So I definitely don't think that this exhausts the equilibrium reasoning. What I do think is it reveals like very important structural features of, I think, equilibrium reasoning more broadly, and I think it would also apply to this case, right? I mean, I don't know too much about Da Vinci, to be honest. Like, and I have to think about it. And I guess like Michael will have something to say probably about conservation principles in the 17th, 18th century. So my sense is that you can tell a similar, like here, I mean, I want to say we are interested in the perturbations, right? The perturbations is all of geophysics, right? Like, and we bring them out by, like, the way we have to make those systems tractable is treating them as being in states of equilibrium, because that makes this very potent machinery of Newtonian mechanics applicable and allows us to reveal those sources of disequilibrium or perturbations that stand in interesting counterfactual dependencies that are robust independently of the theory being true and the models being true. So in that way, I can see why you're saying conceptually that initially when they're thinking about it, those pull in different directions, but I think methodologically they're more alike than you think. Of course, like then the like very local concerns about like perpetual motions machines and so on and so forth, that might be very specific, but if you zoom out and think about like the long-term development of like conservation reasoning, I think you can find at least similar tendencies to the ones that you see here. Wherever, because really we care about the perturbations. That's the point, right? Like we want to figure out something about them. That's how we make the system tractable, by treating as it being in equilibrium. Yeah.